Good evening, everybody. Welcome to yet another online June Norwegian Forum for Offshore Survey and Positioning online event. It's a beautiful evening here in Bergen. I trust there are lots of people looking and viewing in. We have an interesting array of presentations this evening for you, so anyone who's not looking will be definitely missing out. I think what I will do this evening is we have very good, like I say, three very good presentations. The first from Terratec, the second from 3D at Depth, and the third from Vaarst. What I will do shortly here is just give you a quick introduction to NOSP and what we're about. For those that are a little bit unfamiliar, I suspect most of the people looking are actually very familiar with what we are about, but a quick overview of who we are and what we do. Here is a list of all the sponsors that make this all possible. We have a new team in NOSP at the moment. We have six new members. One of our old chairman, Selena, has left us, and I would like to take the opportunity, because I think she's listening and watching, to say thank you for her efforts over the last 7 or 8 years in NOSP for bringing it to where it is now. I have the unenviable task of filling her shoes and carrying it forward, but I have a new team of people to do that, Ricardo and Derek. So, and together with Odd and Martin and John Vint, we are 6 people volunteering on a basis to get these presentations to you. And we do have some good ideas for the future, so I would stay tuned to our website and the LinkedIn page, which I didn't update on this one, unfortunately. But yeah, it should give you a good idea of what we're planning for future events. This is the last one before the summer break, and then we will hopefully have one in August. If not one in August, there will be one in September. So I just would like to mention that, as usual, any one of those sponsors, because we're all naturally gravitated towards online and things aren't quite the same as they were when we were having in-person visits, we have therefore cut the sponsorship price. So if anybody is interested in sponsoring NOSP and the good work that we do, then please do not hesitate to contact me as chairman or any of the others of the members of the board, and we will negotiate a half-price sponsorship deal for 2021. And of course, those are already sponsors, their cost is half anyway. I would encourage anybody in and watching to join the chat room on Discord. The link is below the YouTube link that you're looking at the moment. It's also on the website. So fingers crossed, you will be able to find that and go over there. There'll be a lot of people joining that. I've been there before, and it's a good opportunity to meet up with some people you haven't spoken to for quite a while. And also, if you have any questions to the interesting presentations that we're going to have this evening, you can ask them there. I have my man Ricardo looking after things, and he will feed me some of the questions. So I would encourage you to go across there and look into that. We are, as ever, always looking for people to speak. I think we've got some interesting evenings lined up. I'm always looking to try to get similar presentations so that we have themes of evenings. So if people do want to say something, and that is regardless of whether you're working for a company or if you're a student or you're doing anything along those lines that you think is valuable to the industry, and or potentially interesting for other people to know about, please get in contact with me and we will try to put this together. So that's all I had to say on this front. Just a little bit of an overview of what we have actually coming up in the next couple of months. As I mentioned, on August the 12th, there is a to be confirmed event for us. On the 2nd of September, God willing, we are back to some semblance of normality away from COVID, and we can gather in person down at RTS in Ockram, and we hopefully will have a barbecue, and we'll have 3 or 4 presentations ready for them, and that should be and has been historically a very good event for everybody. So I hope that things have returned to some normality by then. Let's just keep our fingers crossed. So that's all I've got on that front. I now have the pleasure of bringing in our first presenter of the evening, which is Charles de Jongh from Terratec, based in Oslo. Good to meet you, Charles. You've been working for Teledyne for many years, I read, and you've been working for Terratec for the last couple of years. Just tell us a little bit about yourself then quickly, just briefly, before we move on.
Well, good evening, everybody. Yeah, I've got a background in GIS and cartography, and I've mostly worked for the software company Accuracies, part of Teledyne now. That's making software for maritime mapping, and I've worked for many hydrographic agencies in that capacity.
Okay.
And after moving to Terratec, I became sales manager for Bathymetry, and I'm currently focusing on Bathymetric Lidar, being based in Oslo, indeed.
Perfect. Thank you very much. Right, well, your presentation is called The Advantages of Airborne Lidar Bathymetry, and I'll just bring up your presentation. There it is, and I will leave it to you. The floor is basically yours.
Thank you very much, Stuart, for your introduction, and also thanks for the opportunity to have a short presentation here at this NOSP meeting about airborne bathymetric LiDAR. I will start by giving a short introduction to Terratec and basically the broad range of geospatial services that we offer. Terratec is one of the biggest geospatial companies in the Nordic countries, and it has always been at the forefront of technical development. I work in the Airborne Data Capture department, where we have quite a few years of experience with airborne LiDAR, both topographic as well as bathymetric. In this presentation, I will focus on airborne LiDAR bathymetry, what it is, how it works, the types of equipment, and what to take into account. And I will also talk about a specific use case at the Norwegian Hydrographic Service. So airborne LiDAR bathymetry is a remote sensing technique for measuring the depth of relatively shallow coastal and also inland water bodies with a pulsed scanning laser from the air. The technique has actually been around for quite a long time, for more than 50 years. And it was basically first used by the US Navy in the Cold War mostly, to use lasers to find underwater submarines, well, mostly Russians, I guess. And it was all classified. However, in the 70s, the technique already got commercialized by the company Optech in Canada, now Teledyne Optech. And there were, from the beginning, other countries involved as well, with experiments, etc., for US, Canada, Sweden, and Australia. And well, since that time, of course, the technique has evolved tremendously, mostly with faster and more precise lasers and better measuring equipment. And what can be noticed if you look at the current market for airborne LiDAR bathymetry, is that it's really a niche market of airborne LiDAR. And most surveying is done on land, topographic surveys, for example. And also within hydrography, it's a bit of a niche market because most surveys are multi-beam surveys. So furthermore, most organizations that are currently in the world executing bathymetric LiDAR surveys are in the Western world, US, France, UK, but also South Korea, Japan, Australia. And most of it is done by government agencies or companies that work for them. And actually the number of, let's say, available systems in the world is relatively limited, maybe not more than about 25 or something. So it's a bit of a niche market. What I'm doing in this slide, I want to do is to look at what the advantages are of airborne LiDAR bathymetry, mostly when you compare it to, let's say, a regular bathymetric survey with a multi-beam echo sounder. One big advantage, of course, of this survey method is that it's fast. You fly over an area with around 200 to 250 kilometers an hour, which is about 10 times as fast as when covering an area with a ship. So an area can be surveyed much faster than with a multi-beam echo sounder, and also with a wide and nearly constant swath width. You can actually see that in the picture as well, that, well, you fly usually around 400 or 500 meters high. So when you survey in a small, shallow area, the SWOT width is pretty equal compared to when you survey from the water. It's quite a difference what the SWOT width is if you survey 10, 20 or 30 meters with a multi-beam. Also, again, for the shallow areas, it is of course a safe method, right? It is a safe method for surveying areas that are very shallow and difficult to reach, or even impossible to reach with a multi-beam. Another advantage is that you can simultaneously, also shown on the picture here, map the area on land with a high point density as well as in the water. So it gives you a seamless topo bathymetric elevation model of the coastal zone, which is very difficult to achieve with other means. And in a lot of countries, it is actually the coastal zone that is most important to map, because that is where most people live, and that is where most economic activities are. So clearly, there is a lot of value in airborne bathymetric lidar, specifically in the shallow 0 to 10 meter depth area. So also, though, there are some limitations to bathymetric lidar. Clearly, when you survey, the depth that you can reach is depending on a number of variables. First of all, the local water transparency and the turbidity, the reflection of the bottom, and also the strength of the laser pulse. The best systems that are available can reach about 3 times the visible water depth. So based on these variables, the range of depth that you can reach is varying enormously. It can be 1, 2, 3 meters if the water is very muddy and absorbing all the light, to about maybe 70 meters deep in optimal circumstances with tropical transparent waters and white sandy bottoms. So it really depends. And but clearly it is a good technique for shallow areas, while multi-beam is better for deeper areas. So in a way, these two survey methods are very complementary to each other, as you can also see on this picture. This slide is showing an overview of different types of airborne lidar bathymetry systems. Basically, you can divide them in 2 categories: the shallow water systems and the systems that are for shallow water but can also reach deeper water. And it's a bit of a trade-off. The shallow systems usually have a high frequency laser pulse, but with a high frequency, the energy, the amount of light in a pulse is also less, so you can reach not as deep. While on the other hand, the deeper systems usually have more energy in the pulse, so less frequency per second, but are able to reach deeper. The shallow systems, I've got an example here. It's a Regal system from Austrian company Regal. They can be used in airplanes, in helicopters, and more there are trials to also use them in a drone. There is a difficulty with using them in a drone, though, which is that the systems are relatively heavy, because you need a lot of energy to penetrate the water with LiDAR. So you need heavy drones with a good battery. And yeah, so helicopters are useful specifically for river environments, for example, if you really need to follow the river. But the bigger systems, the deep water systems, they are carried in an aircraft. So I've got 2 examples here: the Leica Chiroptera and Hawkeye, shallow and deep water, and the CZMIL SuperNova from Teledyne Optech. So with Regal, Leica, and Teledyne Optech, as well as Fugro, those are actually the 4 biggest manufacturers of airborne bathymetric LiDAR systems. and most of them have been in the business for quite a while already. So to tell you something about how it technically works, I have tried to visualize how an airplane, we are using a Cessna Caravan flying with a speed of around 120 to 140 knots at a height of about 400 meters, is shooting out a laser pulse with a frequency of about 5,000 to 500,000 times per second. It goes very fast. It depends a lot on the system that you're using, but in any case, the laser pulse that's being shot is usually, or actually in all systems, using a green wavelength. And the reason for that is that the green wavelength is penetrating the deepest in the water. Other wavelengths, a lot is of the energy is absorbed by the water, so you can't get that deep. At the same time, most systems also use an infrared frequency of 1064 nanometers, which is mostly reflected on the surface to find out where the water surface is. So the infrared is used for the water surface, while the green LiDAR data is penetrating down to the bottom. And while the light is penetrating the water, the speed is reduced. It's still very quick. The light is refracted. Some of it is absorbed, some of it is scattered, but some of it is hitting the water bottom, which is illuminated. If at least the water is transparent enough, the laser pulse is strong enough, and the water bottom is reflecting, as I mentioned. So you need these factors play a big role. So then the light photons, they reflect back into the air and back into the airplane, and there is a detector in the airplane that detects the light photons. And what I think is useful to mention is that, well, a lot of multi-beam surveying, for example, is done with sound. But here we're surveying with light, and light is about 150,000 times faster than sound. So it's in a way a similar kind of technique, but it's also very different. And the time, just to mention, the time that it takes for a laser pulse to shoot out from around 400 meters height, then penetrate the water of, let's say, 30 meters depth and get back into the airplane. Well, in that time frame, the airplane has moved about 2 millimeters. So that's almost nothing. So when the data, the photons are being digitized by the detector, they are amplified and digitized, what happens is that a waveform is created that's basically counting the number of photons that come back at a specific time frame. And what you usually see in such a waveform is the moment. So you see here in the picture the range in air, and then you see an elevation and more photons being counted at the moment that the photons hit the water, but also at the moment that the water bottom is hit. And basically that difference in time, that is allowing you to compute what the water depth is. And just to mention as well, you've got here also the range in the water, which can also be very interesting, the way that the waveform looks in that area, because it could be that there are objects in the water, or there can be vegetation, etc. And the waveform can say a lot about that. So that was basically one pulse shooting out and coming back. In this picture, you see, based on actually our system, the CZMIL SuperNova, we have a SWAT width of 290 meters. It's a circular pattern. So basically, when you're flying forwards, areas and objects on the water are basically hit with the front of the pulse and then with the back again. So you enlighten the area from different angles. And the result is basically a pulse pattern. And depending on the speed and the height, etc., our system reaches about 8 points per square meter for the so-called shallow channels and 1 for the so-called deep channels. And when you do topographic measurements, it's about 12. So this is a very good value for a number of points for bathymetric LiDAR surveys. Once basically you're back in the office with the survey data, the raw waveform information is being combined with post-processed GNSS and also IMU navigation and positioning data to compute the actual geospatial X, Y, and Z position of the returns. And also here the so-called refraction of the water is taken, the refraction of light in the water is taken into account, because the speed of light is not 300,000 kilometers per second, but about 225,000 kilometers per second in the water. So once that's done, you calibrate the data, and basically you get a correct geospatial point cloud that can be delivered to clients, and other products can be derived as well. And maybe it's good to mention that the values that you measure is normally elevation values based on the ellipsoid, based on GNSS measurements. So if you need to have a local datum, a local vertical reference frame like NN 2000 in Norway, or a nautical chart datum like LAT, you need to correct for that using a separation model. So that's basically from shooting out a pulse to a geospatial point cloud that is post-processed in a nutshell. I would also like to tell you a little bit about our new sensor, the CZMIL SuperNova. So CZMIL is an acronym for Coastal Zone Mapping and Imaging LiDAR. It is one of the deep penetrating LiDARs with a very powerful laser. And to give you a bit of context about this sensor and the history, I would like to say that they were developed by Teledyne Optech in cooperation with the United States government for originally the National Coastal Zone Mapping Program. And currently the sensors, the CZMIL Nova sensors, which is the upgrade of the original CZMIL from 2012, they are being used by the US Army Corps of Engineers, the US Navy, and NOAA, and also other government mapping agencies in other countries in the world. And now, as a result, this picture is basically showing how much of the US coastline, which almost everything, has been mapped with bathymetric LiDAR. And by far the majority of this has been done with one of the CZMIL sensors by USAs. And then also, I know that the US Navy has mapped another around 25,000 square kilometers for tactical surveys all around the world. So it seems to me that of all the bathymetric LiDAR systems in the world, it's likely that the CZMIL is the one that has surveyed the most number of square kilometers. So basically, it's a system that can be trusted and has proved its value. And to emphasize that a bit, I wanted to also show this slide, which is based on a document published by the US Army Corps of Engineers, to basically show the public in the US what the value is of what they're doing. And they're basically saying, well, using the CZMIL, we save a lot of money as well as time when we survey the shoreline, when you compare it with traditional techniques. And also maybe to highlight the many different types of products that are being created based on the data. So it's a typical example of how you survey data once and use it many times, not only for example, nautical charting, but also for geological research, for flood mapping, for a lot of storm modeling, and all sorts of coastal zone management applications. Specifically in the US, you all know that the coast has been hit hard by many different hurricanes like Katrina and others, and in Puerto Rico over the years. And it's always been CZMIL surveys that have been done afterwards to do a quick site reconnaissance survey and see what has changed and see where sand suppletion is needed, for example. So the CZMIL SuperNova, that is the sensor we just got at Terratec, and it has been, well, we got it in April, so about a month ago, and it basically contains, let's say, the latest and greatest when it comes to bathymetric Lidar. It has double the point density of the Nova. That's always, of course, important, and that's also what you see in airborne Lidar bathymetry. The point density has increased over the years, right? Still, normally a multi-beam has a higher point density, but it's getting more and more, and also this is the system that has the best potential depth penetration in the world. I'll talk a bit more about it. The accuracies are improved. For example, the so-called shallow channels are within the IHO special order. I also have a quick slide about that. There are different modes to survey with. For example, you can adapt the settings for more deep surveys or shallow surveys, or when you expect a muddy bottom, you would set the settings different as to where, if you put the energy in shallow or in deep channels, etc. It's also, it has Keras processing software. Well, it's of course my old company, but that's software that's being used in many hydrographic agencies. So you can, the results of the data, the products you can make can directly be used in hydrographic agencies, as well as all the attributes you get with it. So this is the first, actually, Terratec is the first commercial company that has this type of sensor, and it's also the first CZMIL type of system that is available in Europe. It has a digitizer that has a very high light photon sampling rate. So every second, there are 2.5 gigasamples, which means there are 2.5 billion samples of the photons that are coming back every second. And basically, because light goes that quickly, that fast, you need to sample it very quickly to be able to see differences in depth. So this is a higher resolution than other systems, and the result is you get a good description of the waveform. In the picture on the right, you can see, well, this is kind of a very old system where, well, you don't find the bottom or you don't find the surface if you're too slow, let's say. At the same time, this system has a very strong but also short laser pulse width. And that is also important, because if your pulse width is too long, your resolution is also low. You cannot detect objects, for example, in a good way. And I try to visualize that here as well. How a short laser pulse width gives you a better vertical resolution, and a waveform here as well, where you show an object. So this is resulting in precise depth measurement and good object detection possibilities. Here you see in the software kind of a combination. This is basically actually one pulse. One pulse gives many different returns in many different channels. The data is divided in shallow and deep channels, and you see all the waveforms created here with these crosses indicating the water surface, and the red crosses here the water bottom. And these crosses, for example, this is rejected data, so some is accepted and some is rejected. So yeah. One last slide about this, also just to mention, for hydrographers, of course, the accuracy of your data is very important. And what I've tried here is to plot both the horizontal and the vertical accuracy of the CZMIL supernova on top of the International Hydrographic Organization, the IHO, orders. So you've got the dotted lines are IHO orders. This one is the top one is the order 1A and 1B. So you can see that all data or the accuracy of the supernova is within that, both horizontal and vertically. And if you look, for example, at the shallow channels, where most data is measured with that, the accuracy is equal to IHO special order vertically, and horizontally it is better than special order up to, well, quite a deep depth. So it's good accuracies of the data. So coming to the final part of my presentation, a use case. So as I mentioned, we received the CZMIL supernova sensor about a month ago, but we had already won a tender in Norway to do a survey for specifically the Norwegian Hydrographic Service for a pilot project that they are executing together with the Geological Survey, the Norwegian Geological Survey, and the Norwegian Institute of Marine Research. So that's the Havforskningsinstitutt. This is called the Marine Base Maps for the Coastal Zone, Marine Kundenkaart. And we will not only survey with the Bathymetric Lidar, but also with a very high resolution RGB camera. We always take high resolution pictures as well, 150 megapixel, and have a hyperspectral camera on some of the surveys. So the aim of the project here is to use new technology to map the coastal zone of Norway in an efficient way, and also to get as much information out of the data as possible that could be useful for these different organizations, creating different types of coastal zone products for basically the benefit of society. So it's a bit of the same as also done in the US with the CZMIL. So it is a pilot project for now, but if successful, the idea is to use bathymetric lidar also to map larger parts of the long Norwegian coast, at least those areas that are suitable for bathymetric lidar. So for this tender in Stavanger, but also actually in SuperNova, the important thing was to cover the 0 to 10 meter depth area with a specific point density. And well, this is of course important for the hydrographic office, because this is especially the area where they have difficulties surveying with multibeam, as I mentioned before as well. So when we prepared for this survey, we made an assessment of the depths we will probably be able to reach with the supernova in this time of year. And it's good to mention that, well, I mentioned the laser strength that the water depth that you can reach depend on, and the local water properties. So specifically, the transparency of the water is important, and the transparency can be, and the water turbidity can be measured by the so-called KD value of a water body, and this is the so-called diffuse attenuation coefficient. So that indicates how much of the laser light will be absorbed by the water. And for every 1 divided by k meters you go down in the water, you lose about 2/3 of the laser light. So low KD values here represent clean water, and high values represent turbid water. So as you can see on the picture here as well, the coastal areas are usually more turbid because there is more sediment and particles in the water. But this KD coefficient is a very important coefficient to look at. And to measure that, there's different methods, but one method is to measure it from space. So you've got, for example, the ESA Sentinel-3 satellites. They have a sensor on board that's called the Ocean and Land Color Instrument, and you can download that data for free specifically from Cloudless Days, and this instrument measures this KD value. So when you convert that to 532 nanometers, the same wavelength as the LiDAR is using, you can derive the KD value. And we did that for the Stavanger area for most of the year, and we saw that around March, April, for example, the KD is about 0.12, which is quite okay, and that equals a visible depth of around 12-13 meters. So that's pretty good actually. The other thing we did to prepare was to do Secchi depth measurements, and a Secchi depth is a disk that it's pretty simple. You let it down the water, and it goes down and down and down, and you just check into how deep can you see the disk, and that is the disk measurement. And we did different measurements at the end of March, beginning of April, 25th of April, and we saw quite big differences, right? This is related to weather and water that's streaming, of course, but algae bloom is very important. If there's a lot of algae, a lot of chlorophyll in the water, you don't have a good visibility. So we were actually pretty lucky because we did our survey around the 25th of April. So the Secchi depth was good. So we hoped for good results. And what you can see on this picture is basically, okay, this is the type of water, the KD value. This is the depth of the water. The red line is indicating the visible water depth, the Secchi depth measurements, and the green lines are the shallow and the deep channels of the supernova, basically indicating what depths are you theoretically able to reach with this system. And the depths we measured around Stavanger, or the expected depths we should measure, are for the shallow channels around, let's say, 25 meters. And we did this survey indeed with focusing on the shallow channels. And this is a quick screenshot I was able to make. This is basically the land area. It's the point clouds. And we were very happy with the first results because we have data of down to 20 meter deep consistent data, let's put it this way, and down to 32 meters maximum we have depths as well. So you see here 5, 10, 15, 20, 25 meter depth contours. So this is good data, and the hydrographic office is happy with this, but this is an ongoing project, so we're still processing the data, and as it's a new sensor, we're also still learning a lot about it. But just to conclude, I would like to say that you can, with Airborne Bathymetric LiDAR, survey large underwater areas efficiently, specifically when you compare it with a multi-beam. And we have, with the CZMIL SuperNova, a very, let's say, top-notch bathymetric LiDAR system in-house. It's an upgrade of a system that's been used and trusted for many years by the US and other government mapping agencies. And well, the initial results we have in Stavanger, but also based on earlier tests that we had done with the system, are very good. They give us valuable data. So basically, we are looking forward a lot to use this survey to in more waters. So that's it for me. If you have any questions, I am of course available now or in Discord or on LinkedIn, email, or whatever. But thank you for your attention.
Thank you very much, Charles. I thought that was very interesting. I think LiDAR bathymetry has been something I've known about for many years, but probably not seen it as presented in this way anyway. I've got a number of questions just off my own back. There's a couple of questions that have come in from Discord. What is the realistic deepest depths you can go down to? I mean, this is is the SECI level, of course, the new speed of sound that we've got to look at for conventional bathymetry. But what is your experience of being depth of penetration or depth of water depth?
Well, no, I think some of the slides in my presentation I've tried to show. Well, in general, I think you can say that the technique is most useful in the coastal zone, right? The 0 to 10 meter, you usually get good data, but it's as I also mentioned, it can really differ from 1 to 2 meters if it's very muddy and all the light is absorbed. You're really depending on the light absorption of the bottom. Yeah. But I think all the time we can in advance do kind of a research. We knew when we were going to survey in Stavanger, this is the expected water depth that you can reach, right? Based on the satellite measurements, based on local measurements. So you really need to take into account the time of year, etc. But yeah, so realistically, it depends really on the area where you do the survey.
So a good knowledge of the actual area is probably
exactly
a precursor to doing any additional work.
Very
so
important.
How many square kilometers are you able to survey per hour, do you think, given this methodology?
Yeah, well, also that depends a lot. Well, it's definitely faster than multi-beam, but I would say also here it can change to the most optimal would be around 50 square kilometers an hour, right? But there can be cases that it's only 2, 3, 4 kilometers an hour, and that is mostly depending on the length of the flight lines. So if you basically have one flight line straight away, 1 hour you fly straight away, you would do about 50 kilometers an hour. But every turn you make is taking about 2-3 minutes before you're back on the next line and back on the next line. So if you have 15 flight lines that are each 5 kilometers length, and then you need to turn again, then it's just a couple of kilometers an hour. So also here, big differences.
So I presume, comparison-wise, you've got a plane. Is your plane is it fully mobbed all the time? Is that how it is, or do you actually charter a plane? Is your plane ready to go at any time, or is it kitted out with this equipment on a regular basis, and then you just take it on a route? You said you own do you own the plane?
Yes. Now, well, Terratec owns about 7 different planes. So we have a lot, but there are 2 different aircraft in which the CZMIL fits, and that's specifically an aircraft. One of the bigger ones, but also with 2 hatches, so we can combine the CZMIL sensor with, for example, a hyperspectral camera or an even better topographic LiDAR or other. But currently, the CZMIL is ready to go. But it can be that the aircraft needs to be used for something else. But we own the aircraft and all the equipment.
I presume, we're talking autonomy and Yeah, trying to simplify operations, all using drones, I presume, for this at the moment. This is,
Yeah.
I think, a question from Nathan, or is it Vern? I'm not too sure which is his forename. Is a drone usage is not really viable here. The equipment is too heavy. The batteries are too bulky. We're a long way from doing that sort of work at the moment.
Well, it depends on how there are a number of sensors. There's an Astrolite Edge and the Regal sensor that I showed can be used on a drone. Yep. But you will not be able to penetrate very deeply. And for example, I know from the Regal that they had done tests where they were able to survey for about 10 minutes with the drone, right?
Okay.
So you are currently not able to survey large areas with drones. And I am not sure whether that will change a lot in the future. And that's mostly because if you as I mentioned, you need a lot of light, a lot of laser power, bigger instruments to be able to penetrate the water, right? So the drones that you have, they are not able to do a lot of depth penetration. So they have value for some parts. And one last thing regarding drones is that they are, of course, also not a very stable platform. So the data that you get out of it might not be as good as a stable aircraft, for example.
Yeah.
So that's all things to take into account.
Okay, thank you very much. We haven't got any more questions at the moment. I've just got one more. Your presentation was entitled "The Advantages of Airborne Lidar." What is the one big advantage? What is the one big takeaway that you would say improves or is better about this LiDAR bathymetry than other conventional methods then?
Yeah, no, I think that the one takeaway is again that there are very shallow areas in the coastal zone where hydrographic agencies and organizations, they can't reach it easily with a multi-beam, right? And also the SWAT width of a multi-beam and also with AUVs, etc. It's so small when you're so shallow that it's difficult to survey amongst all kinds of rocks or coral or whatever, right? When you fly over it with an airplane, you do it very quickly, right? Yep. So it's economically the way to do it. Yep. And as a bonus, you also get a seamless model of land and water. So for coastal zone management applications, it's the thing to do. to
Perfect. I think there are a lot more questions. I have got a lot more questions, but we're already well over time. You were true to your word. Your presentation took half an hour, a little bit more, but I think it was very interesting, and I thank you very much for your time, Charles. So I'll remove you from this, and I'll bring in Neil Manning from 3D at Depth. Good evening or good afternoon to you, as you're in Houston at the moment. Neil, nice to see you again. Thanks for taking the time out of your very busy corporate schedule to do a presentation for us. I remember I looked at your bio, and you've been in this business about the same time as me, actually. And I started looking at it and thinking I really should have got out and done some more stuff. You've had a very colourful career to date, and ultimately it's at 3D at Depth at the moment. And we had a very good presentation and demonstration in a tank here in Askøy a couple of years ago. So looking forward to this presentation to see where it takes you. Was there anything you'd like to say before we kick in, or should we just get on with the presentation, Neil?
Yeah, well, I mean, obviously, thanks for hosting us year on year. We've enjoyed presenting at the RTS event. Yeah, we enjoyed the NOSP event in Norway with Horsøy that we helped to put together. And thanks for continuing to push, the survey requirements in the region. And we get as difficult, and we've done virtual conferences and had 2 people dial in, and we've done other dial-ins and had a lot of attendance. So we know it's difficult, and I'll go as quick as I can so you guys can get out and enjoy the sun as fast as possible. How about that?
No. I say take your time, because I'm sure this will be very interesting. So I will leave it with you and the audience, and speak to you in about 20 minutes.
Great, thanks. Well, anyway, thanks to everyone again for dialing in and taking the time. The presentation, ironically, will fit really well with what we've just heard. And then for transparencies, when I'm referencing in this airborne practices, it's not like penetrating water. It's just pure topography mapping. So a further niche on top of that is the slide deck that you've just heard, which was quite impressive technology. So for those of you that don't know anything about 3D at depth, we're a subsea LiDAR business. We work primarily in deeper water environments, certainly deeper than what you would see in the topographic zone along the coastlines. The main reason for that, as we've just seen, is water turbidity, and the value of LiDAR in those environments for what we actually utilize LiDAR primarily for would be less recovered. So we started the company. We've had 6 US patents issued. We have a few patents pending, some actually in Europe and Norway. But there's a total of 21 patents wrapped around the technology that are either issued or pending. So unique to us is we're a small business. We design and develop our own technology, and we then operate and service it. So unlike other survey and inspection businesses, we're heavily leveraged on the technology side as our fundament and less on the service. But we want to maintain that closed loop. Since the NOPS events, and I'm sure it's because of some of the exposure from the NOPS events and the partnerships with companies like Subsea 7 and now Equinor, we've been completing some successful projects in Norway. So our footprint in the region has generated more success. And it's also taught us what a country like Norway is doing, and has always progressively pushed new technology. The adaptation of new technology is received very well. So for us, there's a lot of value in being part of NOPS, and these are some of our repeat customers. So tonight we're just going to talk about aerial mapping, and then how that propagates to subsea mapping and some of the problems. Airborne LiDAR went first. We've just heard, it was in the 70s, and in the 60s it was more closed loop, but they went first, and they also were very large, very expensive products to build. And even today, from what we've just seen, it's still a niche market, even more niche if you're penetrating through water from an airborne platform, which is impressive in its own right. And then basically the automotive industry came in, and when the automotive industry took an interest in LiDAR, there was significant investment. I think they invested $4 billion about 3 years ago or 4 years ago into LiDAR, trying to pull the cost down, because there are benefits with LiDAR in terms of range than there is with a camera system. You still need a camera system, in my opinion, and you still need to fuse those data sets. It's just for the application that they needed it. That was what it's for. We'll kind of look at why we even bother with it, and where's the value, and there is an important value in it. And then, what are the possible options for it for the future? So here's kind of historical things, and it shows the status of them and where they're used less now. But all over the planet, and specifically there's a lot in the US, there are these ground calibration targets, and they were used for aircraft using high-end optical systems to calibrate. So, you can also get a NIST scale bar, right, for small tripod type scanning to calibrate and give you a truth. And the value of that is that it helps close the loop on a measurement. And then, if you look at them, you can see, well, this one's still relevant, and it's flown from a drone. So much lower altitude, much more clarity, but it's covered in trees and shrubs because they're no longer used. But camera systems have significantly moved on as well. And this is kind of interesting and relevant to what we'll see next is you can buy software now that, from the Google Play Store, and download it, and iPads, iPhones, and other smart devices, they maintain the computing power to create a 3D SLAM map in real time. And this company is a German and US based company, as an example. And on a mobile device, they can create a SLAM map, move it into a cleaned and processed surface, apply normals to cylinders and flat surfaces, and then export into CAD, all from a phone or an iPad. And it's phenomenal when you think about where technology is going. to what you can achieve now on a mobile device. And it's the data volume is still large and larger than it was from a historical camera system, but it now has the ability to process and run a full workflow. So that computing power with low batteries does help open that drone market. And this is an example of an old LiDAR system that I'm sure does not penetrate water. But you can see in the bottom left there, the automotive industry took, a LiDAR spread and made it small enough. And that was that $4 to $5 billion of investment that was pummeled in to make it commercially viable. So these are all principles for when we get to the challenge of subsea high altitude scanning, is what we have now, what we need, and where it's going, and how is it possible. And it really follows airborne. And an airborne LiDAR, in terms of flying and motion LiDAR in water, the challenges are the same. The ranges are much greater. We're looking at 20 meters. Airborne is 500 meters, as we just heard. But there's a limit there as well. And it's always aircraft. It's a very expensive thing to get into. The automotive industry came along and they pushed it onto a drone.
Neil, can I interrupt you? Sorry,
Yeah.
Your screen is a little bit too small. It wasn't the same when we tested it yesterday. I wonder if you can, I think it would be better if we can maybe zoom in a little bit so that people could actually read the text. I think can you do anything with that at all? Or is it me?
No. It's a wide screen, so that may be the problem.
That is there any way you can change it at all?
I can disconnect it and we'll see what happens.
Okay, give it another go.
Stay on the line.
Yeah, I'm here.
Did that help?
Not one jot.
So what I'll do is I'll exit the show and then go back into it. How's that?
Okay, do that again. Right. Okay, I'll keep everyone entertained. Or you can maybe just try pressing that again. There we go. I will now leave you in peace.
Laptop rather than I bought a 4-foot wide screen.
All right. Good. I'll leave you in peace.
So we were talking about airborne LiDAR and how the automotive industry has dropped the price down and made it affordable. There are trade-offs in this process with everything else. We just spoke about stability. A large aircraft is obviously much more stable than a small drone. The biggest problem is with LiDAR on its own is, you get a wide area mapped, but you don't know, as an example, the house number. You don't see the close-up detail, where the following slide deck should hopefully help build on that, being a camera-based system. So, but you can map areas good and you can monitor. So the problem we have with this principle in water is we're using water as a medium, and we have to propagate light through that, and that's restrictive. This is an example of a project where there's the range to the targets are 12 meters away. The camera can't see it with ambient light on its own. If we look at the same scan location from what the LiDAR can see, we see a lot of clatter and stuff around, but we still don't get to see the target. The good news with a pulse laser system is the pulses will move through and beyond, even in cloudy water, to help with that. We just heard about the higher systems can penetrate 3 times the water depth that the camera can see. And this is an example of that and how that happens in real world. And then once the data is cleaned, there's no degradation to what's behind it. There's just several pulses from a multi-return that a LiDAR system will give that will allow that. So yeah, the biggest problem is that when we look at this presiding slide, we can model the surfaces, we can measure, we can take a volumetric measurement of an anode. In many cases, you can see cracks of a few millimeters or less, but you won't see pitting at the level a camera would see pitting. So if you were looking at a flange face and wanting to establish what was the corrosion or the pitting damage on a flange face, a laser system which is pulsed would struggle with that in comparison to a camera. So for me, that's what we consider object resolution and object clarity. And speed isn't always the answer. The good thing with speed is with speed, you can achieve, you know, you're pulsing at some rate of knots. And because I've dropped to one screen, I've lost my notes at the bottom of the slide. So I'll try and memorize what I was going to try and put across. If you're pulsing at 40,000 measurements a second, that's your limitation. If you increase that to a factor of 400,000, you can average those points. And then that speed and collection can reduce the amount of motion effects in the data. And that's why drone data is becoming more viable in many regards. The disadvantages, and it's not really a problem for drones right now because of power consumption anyway, is if you run at 1 million points a second and some LiDAR systems are running and they're affordable at 1 million points a second, that's outside of the high barrier to entry systems that require, you know, a larger aircraft, a lower power source. With the speed of light in a pulse system, you can only achieve about 150 meter range. And it's just how fast light is moving through air and back again. If you have a high-end system, which is probably what we just looked at right now, you can then achieve a longer range because you can handle multiple pulses without interference. So it's kind of like a sonar. If you ping a sonar in water and then you ping again immediately, you'll see it in the opposing scan, unless you have a way of time syncing and measuring those points. So for scanning on a mobile device subsea, we believe that faster scanning is required. The business has addressed that, and we will be launching a faster scanning system towards the end of this year, and then an increased speed on the system next year to take us up into that 400,000 points a second. We believe with that and sensor fusion, that's what's required to retain, you know, high quality data very quickly from a high altitude. And a high altitude for us is, you know, 15 to 20 meters in water, not obviously 500 meters. I wish it was 500 meters. The biggest value there is collection times will, you know, they will actually decrease, not increase. So that's a typo. And, you know, from that, a 3-hour task will be less than 40 minutes. We'll be able to fly at 5 to 6 knots and collect the same type of data we were collecting at half a knot without any degradation. And if we are going slightly slower, we can average more points on the target and average and clean. So to try and put that point across, I thought, where have we done this before to try and show it? And we actually did it in Norway, and we were in the pit before the Horsøy event with NOSP in 2019. And we spent several days just doing testing and moving the vehicle around and looking at it in comparison with static scanning from a tripod to look at range and noise in the point cloud. So this was a static scan, was taken over probably 3 minutes looking at the size of the data set, where if we were to achieve that now, that would be about 20 seconds. But it's very high resolution and more than you really need if in many cases to pull a measurement. On the bottom of the structure, we had some control points, which I'll circle my mouse on them there. And then we did the same thing with the LiDAR scan, but we scanned much faster. So less points were put out and the mirrors moved a lot quicker. And then we took the measurements again from those. And what we were doing here was experimenting on if we could do a fast scan with the resolution of a high resolution static scan, we would obtain much more averaging, our range accuracies. So even between a fast scan and a slow scan, the difference from the vehicle moving over a short instance in time was a few millimeters, 3 millimeters in 2 planes and 1 in the other. The delta there is you can see the resolution is less. So you can achieve a measurement, but you can't achieve a resolution. With the new scanning electronics that we've developed in-house, we can now achieve resolution in far less time. This shows what a 60-second scan looks like, and we force the vehicle to move to show how the point cloud and the time of flight system is noisy. So if that scan was achievable in 1 or 2 seconds, then we wouldn't see that degradation and we'd still achieve resolution. And we feel that these are all relevant when you extrapolate those back to a flying or high altitude scanning. So it's very similar to aircraft. Aircraft and drone data became better when they scanned faster. This is the scan from the tank, just from a memory standpoint. So this was a fast scan of about 2 seconds. And that's what it took to achieve that. That now would be less than 1 second with the, or we do it over the same time and just, you know, multiply the resolution by 10. Here you can see the leak that was issued in the pit. And this was a medium speed scan. And you'll see along the bottom, we have gaps in the data. That's the vehicle moving, the bubbles creasing to the surface. So with the new electronics, we can scan this quality data in the same time as the previous scan. So it maintains that, and that's the kind of removing the movement of the vehicle. So, you know, why bother with it? Well, we still need to inspect subsea and continue to inspect. So asset integrity is the prime reason. We're also looking at faster scanning speeds will enable positioning relative to a target, range to target, or a target moving relative to you. You need to scan faster to be able to achieve that. And the biggest driver the company has now is preventative value adding. You know, so we can reduce carbon emissions, but still add more value. And a driver for that is to scan faster. We're there less time. You're getting more data for the same cost. But then you see significant reductions in carbon or vessel costs. And then to draw back to the automotive industry of what's driving this is if you look at a Tesla is basically a survey skid on wheels. You know, it has a dead reckoning system on it, which is effectively inertial. It has an ultrasound, it has a Lidar, it has different light level of cameras, night vision cameras, 3D cameras, invisible cameras. So if you look at what a Tesla does, and you could move the data from the Tesla back to the cloud, and maybe that's already happening and we don't know it, you're effectively, by driving, you know, to go buy groceries, and you're taking a Tesla, a Google Earth camera. So the same principle goes with vehicles and data fusion. So here you have Lidar cameras, you know, ultrasound, maybe they could put a ground penetrating radar on there. And then the Sabertooth systems that we've invested in, they carry that impressive payload as well. So our principle is high altitude scanning and merging of multi-beam cameras, side scan sonar if we need to, sub-bottom profiler. And here's the data sets in real world. These are the vehicles that you saw in Norway that then moved on to France afterwards and collected data. For this particular project, they had several different campaigns. They ran it up to a Drix and then back to the shore. But there was a lot of high altitude scanning achieved. And then the last comment on this is to think about what we can collect with LiDAR now, what we can collect in the future in a faster time. And then if you have the luxury of planning, you can take terrestrial laser scans of objects and then register them subsea. So this has been started for inferred metrologies on projects like this. So we're achieving inferred metrologies. The value afterwards is if you can combine the sensors that are in the tree or a manifold with a photogrammetric image and a LiDAR flying at high altitude. When you look at all those different sensors that are coming into an integrity system, you know if you've got a leak potentially because of the tree and a flow meter on a tree telling you there's a leak, that can be validated with high altitude LiDAR. If you have a temperature problem or a thermal expansion, the LiDAR and some of these other sensors on these structures can help with that integrity plan. What it can't do is you can't take, obviously, a subsea photogrammetric image and place it on. If the tree is already installed and then we're just doing a life of field map and it's what we would consider a brown field, we can't offer photogrammetric, but you can achieve that with what you're going to see next or with other laser camera manufacturers. So you can get that very close detail, do that to build a baseline and a digital representation, and then take that forwards. So that's the value of high LiDAR. I believe we'll be able to do well site maps in, less than a shift offshore. So a few hours from a high altitude scanning LiDAR merged with these other data sets, and then that fused with what's already inside the subsea production systems will generate value for high altitude scanning. And here's what it looks like when you register it together. This is obviously still during installation phase. The jumpers aren't installed. Very rarely do we go back immediately afterwards. So we never get to see the jumper installed until 1 or 2 years later when they want to do some integrity checks. And then this is another blast from the past, but it's real now in terms of a product line. The goal is that we have the Lidar running on the Sabertooth, and we can achieve these in near real time. That's the end of the slideshow.
Thanks.
I lost all my notes for every slide when I went to a single screen.
Apologies if I feel guilty.
That's okay.
Only a little. Very interesting. I think I'm most interested about the concept of the Sabertooth, purchase of the Sabertooth. The Sabertooth is your Tesla Model X, as you put it, and you're essentially, it sounds like there's a lot of repetitive work you can create from this. So you go out and you're charting the field as it is, and then come back a couple of years later and everything's relative to how it was then. So there's a lot of continued work for you with this, do you feel, with the acquisition of the Sabertooth? Is that something that's kind of driving it a little?
Yeah, I certainly hope there's repetitive work. Otherwise, we'll probably wonder why we bought it.
Well, what I meant by repetitive work is in same fields. So keep going back not on an annual basis, but a biannual basis, and then monitoring for changes because of the high accuracy that you're achieving. Is that fair to say?
Yeah, so we're doing that today with work-class ROVs. You know, we've got one Sabertooth, and there may be another one coming. So we're not going to manage our market for that. The value of the Sabertooth is the speed on location for us, and then fully integrated, the navigation suite, the timing, everything is on board the vehicle with an atomic clock. And the challenge when we hop from vessel to vessel of opportunity and other third-party survey spreads is the mobilization time. So we believe with the faster scanning, we'll be able to achieve with the stability of the Sabertooth good enough measurements to look for change over time in the order of millimeters of lateral or rotational change from one structure to another. But it will never replace a static scan where you want to sit and stare at something for a long period of time. But if you have, you know, a blend of what's coming up in the next presentation or an optical representation and we're just looking and trying to scan only those control points, which we can do really quickly. And when you start to fuse that data set, then that's what you can achieve. And that's what we hope to do with the Sabertooth, is put a camera point cloud system on to complement the Lidar and the multi-beam.
All right. We were talking before, and you're based in Houston, still doing obviously a lot of work in the oil and gas. Are you seeing more work potentially coming your way in the renewables now for this type of, as the evolution of renewables takes place, and it's still in its infancy in some countries like the US? Are you seeing that people are understanding the need for this type of technology to give them the information that they require? Or is it still the oil and gas?
I mean, the benefit renewables has in the US market over oil and gas is renewables in Europe is not new. The operators here on the East Coast are primarily pulling expertise, or they're even headquartered in Europe for renewable energy. So they have that head start. You know, they're not learning again. The installation cost right now, the cost of surveys and inspection will have to come down for the renewables market. And they'll also have a shortage of people, which we were discussing before this call, and the lack of availability of surveying staff. So they'll only achieve that with autonomy. They won't be able to maintain the pace because the market can't serve them. And if the west coast of the US turns on quicker than expected, which with current administration is a full potential there, then they'll only achieve this with autonomy.
Very good.
We feel that'll be a driver.
It'll be very interesting to see what Mr. Biden does over the next couple of years. He certainly seems to have deep pockets anyway. So, although that needs to be ratified, doesn't it? But to put it mildly, just from an operational perspective, does the LiDAR respond to average like water turbidity conditions? I mean, how much does that affect operations for you if it is murky water and the maintaining accuracy?
Accuracy does not change, but range does. Scanning faster helps actually, because we can average more points in a single point where the mirrors dwell, and the mirrors are dwelling for, nanoseconds, not milliseconds. So it enables us to hold the mirrors in a position and then move them, but collect up to 10 times the amount of points to pull on average. Some of those pulses go further through the water on that transmit before we rotate the mirror. So we don't lose accuracy, but we will lose range, which is why we, advertise 20 meters. In the Gulf of Mexico, we generally see 25 meters or a bit more. But if we come shallower, you really do see a drop off. So we have to move the vehicle closer to the object.
I remember from the Horsoy event that that pool was not exactly clean. I wouldn't have jumped in and gone for a swim, but you were picking out stickers on the side of the drilling head. I thought that was remarkable to see. So a very, very interesting bit of technology that you're obviously evolving on a daily basis. So thank you very much. I haven't got any more questions. It's incredibly quiet on Discord tonight. So if there are any other questions, I know you're available for more if you're in Discord and elsewhere. But Neil, thank you very much for your time. It's always a pleasure to talk to you. Very interesting technology you have there, and we look forward to speaking to you again. Okay.
Thank you. Thanks. Bye.
Bye-bye. Right. Okay. Thank you very much to Neil and to Charles. So we're bringing in our third presentation this evening, which is Alex Steele from Vaarst. I was completely unaware of this company up until about 2 weeks ago. So, Alex, this is an opportunity for you to present SLAM ×2 or subSLAM. I'm very naive on my understanding of SLAM. It sounds like when you say the acronym, it takes my mind somewhere completely different. So this is an opportunity for you to present to me and to other people on the call a little bit about what Vaarst does and the technology here. So good to finally meet you, and thanks for taking the time. I see you've got history from Rovco and still to a degree involved in Rovco. I'm a little bit confused by that relationship, but I'm sure you'll allude to it in your presentation. So let me just bring up this one. There's yours. And Alex, I think, the floor is yours. So take it away. Thank you very much.
Perfect. Thank you, Stuart, and indeed Ricardo for inviting me to join you all on this fine evening. I can appreciate that the weather is very nice in many parts of the world, and so we'll try and keep this to time, despite being able to talk tech all evening if we want to. As with all of the presenters, I'd encourage those of you who wish to know more about any of the topics that we've covered this evening to feel free to reach out to all of us afterwards as well. So, a bit of kind of introduction. My name's Alex Steele. I'm the Global Product Manager here at Vaarst. As Stuart mentioned, Vaarst has only formally launched recently. However, it already existed as a stealth business within Rovco right from its inception in 2016. So this year, in 2021, Vaarst was formed to commercialize the simultaneous localization and mapping, so SLAM, developments that we'd been undertaking. Also looking to commercialize our machine learning roadmap and also the autonomy learnings from Rovco as well, and use those to accelerate the transformation of marine insight, and with it, key areas of the global economy, including connectivity and the energy transition as well. So Vaarst's mission is to enable data to drive the future of marine robotics. By developing technology across multiple areas, we aim to give all offshore robotics, whether on the surface, under the water, or in the cloud, enhanced capabilities. And these enhanced capabilities are really driven through artificial intelligence, machine learning, and autonomy. And crucially, are all developed within Vaarst to integrate with marine robotic vehicles that exist already. So both new and as a retrofit solution to existing vehicles. We're going to focus on two aspects of our technology stack during this evening session, starting with our 3D visual SLAM technology, before showing some of our latest developments and how this has evolved to feed into the drive for autonomous navigation in the marine environment. So subSLAM X2 is one of our flagship products, and it can be seen in the image on the right. And it's a SLAM, or simultaneous localization area and mapping perception system. Its small form factor and weight allows it to be easily mobilized onto vehicles of all sizes and enables advanced computing to be run at the edge. And what we mean by at the edge is on board the subsea vehicle rather than on the surface or back in the control center. By having two high-grade imaging sensors rigidly located a fixed distance apart by a patented modular design of housing, we're able to obtain a 3D map of the world around the vehicle, essentially acting as the eyes for ROVs as they move around. So this 3D map is achieved in real time with millimetric accuracy and generates a true colored point cloud that can be used for advanced analysis of assets condition without requiring any external input, such as LBL or INS or USBL, etc. By moving the compute subsea, we're also able to fully integrate subSLAM with the control loop of the ROVs in order to drive that autonomous nature. So we use this closed feedback loop to not only model the world, but also control the vehicle itself. This is possible in both a standoff position and position hold mode, as well as for close range navigation. And it's something that we'll touch on in much more detail as we go through this, this presentation. And combining our 3D perception system with the autonomy and our machine learning developments, we've been able to train the system to detect objects of interest, for example, anodes, which then helps inform the operator where to move the vehicle to, what they should be doing, what they should be looking at, in addition to collecting the information surrounding the structure's health that the end operator really wants to know about, while navigating around the 3D world that they've built up. So the next stage will be to combine this information to carry out direct intervention tasks autonomously. So based off the information that subSLAM gathers and the control of the vehicle, we can then go and carry out those intervention tasks. What makes the system fairly unique is the fact that it's been designed from the ground up to be retrofitted onto existing vehicles. So enhancing traditional ROVs already in an organization's fleet and bringing them up to a modern standard by having this completely agnostic approach and integration with the control systems allows us to have that wide market and therefore make it approachable. And lastly, the last topic that we'll go into today is the fact that data is all good. You know, we've seen lots of systems can collect some pretty awesome data, whether it's Lidar, whether it's airborne, whether it's visual navigation. However, it all becomes meaningless if it's not delivered back into the hands of the experts. So the subSLAM system incorporates low bandwidth transmission of the 3D data, making 3D models collected immediately available back on the beach in an operations center, or to be honest, even on your mobile phone. And we'll kind of talk about that as we go through. But to break each section down, let's start with the real-time 3D mapping. So subSLAM X2 collects both the 3D point cloud data as well as standard inspection data, such as 4K video, stills images, and it stores these natively either on the camera itself or on the topside PC. This information is used to contactlessly build up a coverage map of the asset or the area, and it can be exported immediately after the survey without any processing at all if you need to. Differing slightly from photogrammetry, which is a tool that some of you may have heard about or used, which requires in-depth processing of the visual data that we're collecting, the real-time output allows the operator to leave site with full confidence that they've collected sufficient information, rather than getting back to the office, processing the data, and actually realizing that you've got a large data gap. So let's have a look at some of the data that subSLAM can collect. And here we can see a sped up version of the subSLAM user interface during a real survey. And in the video, you can see the ROV dynamically moving around the asset. As it moves around, the point cloud's filled in real time with that high accuracy definition that we all like to see. So the system works by detecting individual features within the image, which are shown as the pink detections in the video screen in the top left, while simultaneously providing feedback to the operator regarding how many features are actually in the frame, as shown by that green bar. So those of you observing the model will occasionally see a white message also pop up in the top right-hand corner. And this is the feature where, when the system detects features that have been seen previously, it closes that loop and calculates the misclosure of the model, thereby maintaining the accuracy and minimizing any drift over large areas. So here we can see that subSLAM's completed the boat, it's moved onto the wheelhouse, and it's still tracking. And that's because it's robust at tracking features, even the features that the human eye can't necessarily see. And it can do this across multiple features, multiple surfaces. So as we can see in this instance, the tracking is maintained not only on the assets themselves, but it's also tracked across the seabed floor, allowing the model to be built up over a large area, incorporating, the few sunken vessels and the helicopter and the structure that you can see. So traditionally, high accuracy SLAM and 3D datasets have a large limitation of being able to be collected only over a small or relatively small distance. With Vaarst's real-time dynamic SLAM, we're able to extend that distance to an extent that the limitation is almost removed completely. So here's one example of a model that contains 97 million data points, although we've gone higher than that. That was just for this example, encompassing over 1 kilometer of flight distance and covering an area of 78 square meters. Pretty impressive for a millimetric system. So on the accuracies, subSLAM not only creates that accurately colored model that you can see, but it does have high measurement accuracy. By comparing an object in a dry dock to a terrestrial P40 laser scanner in this case, and then comparing that with subSLAM once the dry dock had been filled, and we had the murky waters of a standard dry dock in a commercial port, we can see that it's possible to achieve that sub-millimeter accuracy, with the model being within the noise of that terrestrial laser scanner. So given the high accuracy, the benefits of and the speed of the data collection, without requiring multiple setups, is sometimes the case with some Lidar systems and traditional photogrammetry, where you lose kind of reference of what you may have modeled and what you may need to go over again. subSLAM is able to collect the data set in minutes while dynamically moving around that object and building up the real-time model. It's not just short-range accuracy as well. So recently we completed some accuracy trials to establish the viability for using the subSLAM system for spool piece metrology work scopes. And this was conducted over a sandy seabed with real-time data collection of the ROV flying, at standard GVI speeds between assets, without requiring any positioning source or INS on the vehicle. These results from the subsea trial were compared to the third-party DIMCON for flanges at low tide, and really speak for themselves. So over 50 meters, we achieved 46.2 mil of accuracy, and over 30 meters, this was 27 mil, all from that real-time data set without any processing at all. With some processing of the data, it's likely that we can improve this even further, and it's something that we're looking at while operations are going on as well. So some other examples of work that's been carried out using subSLAM to date includes estimating the volume depletion of anodes on structures that Neil was talking about, doing Lidar as well. Collecting models across the life cycle of an asset really allows that change detection and the digital twin to be modeled, and you get that base case, and then you can calculate the depletion and really quantify that over the entire life cycle. It allows any maintenance and replacement activities to be visually seen, and also allows them to be planned in order to avoid costly issues if they're left unmonitored. The same applies to other assets, and advanced analysis of dynamic chain wear on FPSOs has been a big talking topic over the last couple of years. And this is an example undertaken by subSLAM on an FPSO, although it could equally be applied to a floating wind turbine as well. And here you can really see the benefit of comparing that triangulated mesh model, that tin model, with the true colored point clouds, so the XYZ RGB, as areas of marine growth are really easily seen, and you can immediately identify what is where by the discoloration of the chain itself. So this is in addition to being able to undertake measurements in order to establish the wear. You can actually visually see it, and then you can look at the interlinks and the bar locations in order to quantify that through the analysis as well. So by using subSLAM to generate the point cloud, we calculate that XYZ position in the RGB. We wanted a solution to be able to send that back to shore in order to get those experts involved as early as possible. And because we're only sending a point cloud data set, it's able to be achieved over extremely low bandwidths of under 200 kilobits per second by only streaming those XYZ and RGB points. However, in order to give the remote user a kind of view into what the operations are going on, we can also send an image at a frame rate lower than the camera is actually collecting in order to aid that visual perception of what they're looking at that time. That can also be used for eventing and those kind of tasks as they're flying around the structure. The locally generated model is available to view through our platform, and being web accessible, this is available on any device capable of accessing the web. So here we can see a remote user accessing that platform and observing a structure being modeled offshore in real time. So the model is rebuilt locally on his PC, which allows him to manipulate the model on their own screen, as well as being able to take those measurements that he wants to see. Now, this gives the user the ability to not only monitor operations, but access experts for advice, have that remote conversation, and make informed decisions quickly between the offshore and the onshore teams. So the way that we conduct survey operations is changing dramatically, with remote and autonomous operations becoming increasingly key. So building on those aspects of subSLAM that we've mentioned, we're able to move away from being just a passive sensor to an active and integral part of the vehicle as well. So by exploiting the high frame rate of the system and its ability to map the environment around itself, we've successfully integrated subSLAM into the control loop of existing ROVs. So this allows the system, once an object's detected in that view, to control the thrust vector of the vehicle and navigate in that challenging last 5 meters of approach. So rather than the waypoint navigation mode, this is the last 5 meters where you really want that high detail and high control. So while understanding that full autonomy may still be scary to some, although we're seeing that starting to change within the various industries, we have developed the system in a two-tiered approach. So these two categories are supervised survey and fully autonomous survey as well. And by making the piloting of vehicles easy, operators are then freed up to focus on the more complex tasks, either locally or through remote piloting as well. So to start with, our pilot supervised autonomy uses that perception system to suggest the locations to the operator. So the operator is then able to select an option, which is shown by one of these gray boxes in this case. And the ROV itself will calculate the direction and magnitude of thrust, and it will then move to that location. So you can see the green line in this video is the track of the ROV, And as the operator is clicking, just simply left clicking on one of these options, the ROV itself is moving. This is also possible even when subjected to currents and external forces as well. So this is one of our test locations with those kind of external forces acting on the ROV, and it's still maintaining that track. So who could have imagined a few years ago that surveying a structure or going over a site would be as easy as clicking on a screen? It's amazing how the technology is moving forwards. For those of you who wish to take autonomous operations that one step further, we've also developed the fully autonomous survey solution. So this uses subSLAM and the control loop within the ROV as well, and is therefore capable of being retrofitted to any vehicle to enhance its capabilities. So by using the SLAM mapper to gain that situational awareness, the ROV will, without user input, navigate around a site. So this is possible using that SLAM system to accurately detect the features, and therefore the relative position of the ROV is accurately known as well, which makes changing terrain not an issue, because as the position hold that we mentioned earlier is able to maintain that set distance from the structure, and this is demonstrated in this video by the fact that as the ROV moves over these raised blue areas, then the ROV alters its depth in order to maintain that standoff distance before just carrying on with the survey as it was before. So that was demonstrated in a simulator on the previous slide. However, we've also demonstrated this full autonomy in a real-world scenario as well. So here the ROV is able to intelligently select the best path in order to accomplish a survey of a surface. So as we watch this video, you can see the ROV autonomously, without any user input, navigating across the face of a quarry, autonomously detecting outcrops and depressions into the rock face in order to maintain that safe navigation of the ROV across the site. So the beauty of the solution, as is often said, is in making truly complex tasks look absolutely effortless. So in this case, we can see the ROV pilot actually being completely hands-off as the vehicle itself is just carrying on with the survey activities. So to summarize, subSLAM is a highly capable inspection tool that can be used to collect information about assets and the natural world, in addition to providing that modular system that allows existing ROVs to be enhanced by edge compute and autonomy. So thank you very much for taking the time to listen, and I welcome any questions that you may have.
Thank you, Alex. I'm floored by that. I didn't have an understanding, a grasp of SLAM before. Now I do. I find the technology utterly remarkable, really. As you said, it's amazing where it's come in such a short space of time, and everyone in offshore needs to be very worried, don't they, really, about their jobs. But just from a technology point of view, is this proprietary software for you? You've developed it yourself within Rovco. This is something, I know that there are other subSLAM offerings out there. This is all Rovco and Vaarst, is this? Yeah, so originally it was developed within Rovco, and it was used and trialed by our operations departments. However, the split between Rovco and Vaarst has now been made, and that's been made with the spin-off company of Vaarst in order to enable the technology to be rolled out across to other companies. So actually this is available commercially today, so anyone could pick up the phone and probably not call me, but probably call one of our sales and business development team, and put it onto your projects and onto your ROVs tomorrow. But does that, and that's kind of what I was actually kind of gearing towards, really, is this is not just for use by Rovco, this is available to the likes of the companies I work for and we work with. I presume that you send off engineers as well offshore, although I know you mentioned some remote operations and autonomous work as well. So it's not just something we would accept from you and expect to run ourselves. You provide support in that respect.
Yeah, so we can do it in numerous different ways. We have had some local training, so we've run trainings for external companies in order for them to get au fait, and then they're going off and running the system themselves without any input from us. However, we can also look at providing some assistance with certainly the early projects if required as well.
And you're seeing a lot of work from the inspection side and decommissioning as well, or is it chiefly inspection, asset management, that your asset integration that you're interested in, or that's the field that you're seeing most of your work? Is that correct?
Yeah, so we're seeing the work in a lot of different domains. Obviously, we've only recently created that split between the internal Rovco and the Vaarst kind of differentiator. And traditionally, a lot of our work's been in the renewables industry. That's where Rovco primarily or works quite heavily. And so we've been looking at offshore wind, turbine inspections, CPS inspections, but also now that we're having that kind of wider market, if you like, with external companies, we're seeing that the market's grown and we're getting inquiries from all sorts of all corners of the globe, really. Yeah.
So on that front then, from an oil and gas perspective, if you're conducting a metrology, is another question that's just come in. Is it required within the system for seabed features that needed to be to gain confidence in the overall building of the picture if you're doing a metrology, or is it just the flanges or what are the distance? How does it require seabed features to do that, to help?
Yeah, so that's a really interesting question, and it was something that we had or we were kind of keen to test out, and that's why during our initial metrology trials we were looking at a featureless sandy seabed in order to see how it would perform and behave. And we were actually incredibly surprised and delighted the fact that with a clean seabed with very little features that were visible, the system was able to maintain tracking and achieve those accuracies as well.
Okay.
So we do need to have a seabed in the field of view. We can't do mid-water tracking. Right. However, it can be fairly featureless without too many kind of rocks and debris down there.
Interesting. All right. Well, thank you very much. I don't have any more questions on my side. As I say, it's been very quiet this evening, no doubt attributed to the phenomenal weather we've been having over here. And you say it's quite good. It's not very good in Scotland, apparently, Mike's telling me. But so I don't have any more questions. I think we'll wrap up the evening there. We've had 3 extremely interesting presentations. I'd like to thank you, Alex, for your time. It's been very educational from my perspective, and I hope other people who took the time to tune in have found it equally informative as well, because that's what this is all about at the end of the day. So thank you very much, Alex. I'll remove you from the line. I'll take that one away. So it's just now, we've been here for about 1 hour and 3/4, 3 very interesting presentations. I hope you'll agree. I will try to get these presentations from the presenters and get them up on the website so that anybody who is curious about the technology that you've heard tonight can go download them and learn a little bit more about what's on offer out in the industry there. So thank you very much for your time, and we will end the broadcast, I think, about here. Like I say, there's another opportunity in August. We're wrapping up for the summer now, so I wish everyone a nice summer, of course, and we will see everyone on the flip side of what will hopefully be a good time for everybody and a little bit safer than it has been over the last year or so. So goodbye from me and the NOSP team. Thank you very much for Ricardo for his support in the background and the other guys in the group, and we'll see you soon. Bye for now.